You build an AI agent on your laptop. It reasons flawlessly, calls the right tools, and generates accurate responses. Then you push it to a live environment. A single server restarts, and the entire system goes completely dark. To prevent this specific failure, OpenAI, Google, and Microsoft have all wired their official agent frameworks to a shared architectural dependency. User input flows into a basic Python dictionary, acting as a scratchpad, feeding context to the LLM. It works perfectly locally, but if a pod dies mid-conversation, the temporary memory shatters, the connection dissolves, and the agent completely forgets who it is talking to. Production environments demand state that survives outside the immediate process. The agent's memory has to outlive server restarts and remain accessible across dozens of parallel instances simultaneously. The solution the industry converged on is taking high-speed data layers, technology originally built for basic caching, and repurposing them as the core state and memory engines for these frameworks. When every major framework from LangGraph to OpenAI's SDK ships with the same specific adapter, it signals a shift in the engineering challenge. Sophisticated reasoning is now available off the shelf. The barrier to deployment is the plumbing required to keep that reasoning coherent over time. That infrastructure requires solving 4 specific problems. The first is working memory, a lightning-fast scratchpad to hold real-time conversational state between turns. The second is long-term memory. The agent must persist user facts, historical actions, and preferences across entirely separate sessions. The third is robust context retrieval. The LLM does not inherently know your proprietary data or customer history, so the system must accurately inject that context at runtime. The fourth is durable state and task coordination, ensuring multi-step workflows can recover gracefully if a process fails halfway through. These 4 pillars separate fragile weekend projects from enterprise-grade systems. They are hard engineering requirements. Working memory is hit on every single turn of a conversation, meaning a slow database write will instantly degrade the user experience. It must respond in microseconds. This diagram shows a pluggable checkpointer saving the agent's state at every microstep, with data pulsing at microsecond latency. If the process dies, a new pod reads the checkpointer and resumes the exact millisecond it stopped. Traditional relational databases struggle here. Storing state on every tool call introduces millisecond-level delays that compound, quickly turning the database into the system's heaviest bottleneck. Integrating a high-speed data layer bypasses this latency. In modern frameworks, it often takes just 2 lines of code to point the agent's execution graph to an external memory instance. Without a dedicated, ultra-fast checkpointer, an agent's working memory throttles the entire operation. Working memory handles immediate context, but long-term memory requires far more processing. The naive approach of dumping raw chat logs straight into a vector database fails quickly in production. True long-term memory means isolating disjointed data and categorizing it into distinct types, separating hard facts from user preferences and past events. Unstructured text flows into the memory server block, which asynchronously analyzes it, eliminating duplicates. It outputs color-coded blocks for topics, entities, and preferences. These facts are converted into vector embeddings and routed to a vector DB for semantic search later. To standardize how the agent interacts with this memory server, systems now use the Model Context Protocol, or MCP. This interface allows the agent to autonomously manage its own memory without custom glue code. Long-term memory is an active, asynchronous structuring process. It prevents the agent's context window from overflowing while keeping responses highly relevant. When it comes to context retrieval, the basic pipeline of chunking documents and injecting vector matches is now an industry baseline. The quality gap in modern agents comes from 4 specific architectural upgrades built on top of that foundation. This Venn diagram shows the first upgrade, hybrid search. Pure vector search finds meaning but fails at exact string matches. Combining semantic meaning with traditional keyword search pathways simultaneously drastically improves initial retrieval accuracy. The second upgrade is metadata filtering. Searching an entire database for every query introduces noise and irrelevant results. Pre-filtering the search by user ID or a specific date range isolates a clean slice of data. This prevents the LLM from hallucinating based on crossover from other accounts. This animated diagram visualizes the third upgrade, re-ranking. The initial vector search acts as a blunt shortlisting tool, catching 50 decent results in a wide funnel. Those pass into a specialized re-ranker node that outputs only the 10 brightest, most precise matches. The re-ranker performs a computationally heavier second pass on the initial list, guaranteeing that only the absolute best context reaches the prompt. The fourth upgrade is semantic caching. If two users ask the same question using slightly different words, executing two separate LLM calls wastes compute and money. Without these 4 layers, an agent operates on blind vectors, resulting in hallucinations, high latency, and wasted cloud costs. This flowchart details a semantic cache. A query splits at a check cache diamond. If it recognizes semantic meaning, a yes path loops back to the user. A tunable distance threshold decides what constitutes a matching question, changing how easily it takes the bypass. On a cache hit, the stored answer is returned instantly. The request bypasses the LLM entirely, incurring 0 inference cost and achieving near 0 latency. On a cache miss, the system takes the no path, calls the LLM normally, and instantly saves the resulting vector and answer to the cache for the next user. In production environments, semantic caching typically cuts raw LLM inference costs by 20% to 60%, depending on the repetitiveness of the traffic. Defining these vectors, schemas, and query parameters is managed directly in Python code using built-in query builders provided by the data layer libraries. This code-first approach eliminates the need to manually write raw database creation commands or maintain separate query infrastructure. Semantic caching is an economic necessity. It makes scaling high-volume AI agents financially viable. We have now defined the complete system, the checkpointer, the MCP memory server, the hybrid RAG pipeline, and the semantic cache. This animated split screen illustrates a common deployment flaw. On the left, teams often spin up a separate, specialized database for every single one of those 4 functions, creating a tangled, sprawling architecture. The choice of vector infrastructure is no longer about raw mathematical speed. It's about operational simplicity and reducing the surface area for systemic failure. Consolidating these workloads is the technical goal. Notice the clean, elegant architecture where the agent interacts with a single, unified data boundary, handling vectors, caching, queuing, and state simultaneously. Leveraging an existing, high-speed, unified layer prevents the need to onboard and maintain fragile new infrastructure just to support vector math. Performance in modern agents is dictated by the architecture surrounding the model. A specialized agent running a small LLM supported by a microsecond checkpointer and a multi-stage RAG pipeline will consistently outperform a massive model running on fragile local infrastructure.
Thank you. Share and subscribe to Learn AI for more AI insights.